So what do you want to do next? We looked at this new device, no?
Correct.
Called an BJT.
Yeah. But we need some equations to use this device. I mean, in
That
this
is
circuit.
true. That is true.
So
Shall we take the voltages and currents?
Yeah.
Hmm?
Yeah.
Okay. Shall we take one? Which device do you want to take?
I like NPN.
NPN.
Hmm.
Okay. We'll take the NPN and do it. So we said this is the collector, base,
emitter.
and some textbooks also I have seen having a circle.
Mm-hmm.
That is also common, no? But I mean, common drawing by hand and all, we don't bother to put the circle.
Yeah.
So we have 3 terminals.
Mm.
We have a whole bunch of voltages, no?
Mm.
So maybe we'll mark all voltages.
Yeah.
Huh?
Mm.
So
VBE.
we have VBE, we have VCE,
Yeah.
and we have VCB also.
Yeah.
Okay. We will also have currents. I'll mark it with a different color. So we have emitter current,
Mm.
we have collector current,
Yeah.
and we have the base current. So we have marked all currents and voltages in the device. Right?
Mm. And the junction that is forward bias is base emitter.
Base
or
emitter
emitter
junction.
base junction.
Correct.
Emitter base. Huh?
Base emitter.
Yeah.
Technically NPN, right?
Hmm.
So base emitter junction in this case.
Hmm.
So we'll also mark that.
Yeah.
So N, I'll use a different color, N, P, N. So in this case, PN junction. So base emitter junction is forward bias,
Yes. Yes.
right?
Oh. So we know some expression for current in the PN junction for the diode.
That is true.
Can we use that?
We should be able to use
Should
that,
be
no?
valuable.
Correct. So we'll write the emitter current now then.
Hmm.
Perfect. We'll write this. So there is some saturation current.
IS. that
IS
we
is what we use. In this case, I'll call it IES
Ah.
because it's the saturation current of the emitter.
Emitter.
We have many currents here, no?
Correct,
There
correct,
we only had one current.
Yeah.
So we'll call it IES.
E power VB.
VBE, no?
Hmm.
So we exponential e power, so basically VBE by same
Yeah.
thermal voltage, no?
Yeah.
KT by Q.
Minus one. We can skip in
We
fine.
can skip
Okay.
it. So we'll just write it like this.
Yeah.
IES exponential VBE by VT.
Yeah.
Because we are assuming that the base emitter junction is going to be forward,
Forward
bias,
bias.
no? That means that it's beyond the on voltage.
Correct. Correct.
Oh,
Hmm.
which means
Oh.
if it is like this, VB is high,
Hmm.
can we just say it is some 0.7 volts?
It could be that range only.
It could be that range, no?
Yeah.
Just like a diode, depending on what material you
Correct.
use and so on. So we'll say,
Approximately 0.7.
so yeah, some VBE on, it's a forward bias junction. There we had V on, we'll have some VBE on.
Yeah.
So let's say 0.7 volts for silicon,
Correct.
right? Okay, this is nice. So when the transistor BJT, NPN BJT, no, is conducting, it looks like the base emitter voltage will be 0.7 volts, right? The emitter current exponentially related to the base emitter voltage. Nice. Okay. So we have at least one set of.
And this current will go to where? Collector mostly.
That is true, because we said we are going to make the device very thin, no?
Yeah.
The base device,
Yeah.
the base is going to be very thin.
Hmm.
So I'll draw it like this. So we drew it like collector and emitter, I think,
Yeah.
something like this.
Yeah.
So if there is some current flowing like this, most of the current, we said we'll make it thin enough such that the current flows only from the collector. So this is, base current is very small, right? That is true. So the collector current is almost equal to the,
It's not equal.
it's not equal, slightly less,
Okay.
right? Correct.
So is there any factor relating to that?
Okay. So we will, shall we use some factor? Alpha. We'll just say alpha, right? we'll just say that IC is some alpha times IE, and we'll say that alpha is less than 1, but very close to 1, right? Alpha less than 1, but very close to 1. I don't know if there is an easy mathematical way to say it, but very close to 1.
Yes.
Right? We'll write it like this.
So very close to 1. So the whatever not close to 1 is going through
the base.
Okay.
Right? That is the unwanted current. We want to design the device such that all of the emitter current also flows through the collector. That would be an ideal device, a good device. Correct.
That
So
is dream.
maybe if alpha was 0.99, then 1% of the current will flow through the base, 99% of the current will flow through the collector. In fact, you probably want much more than 0.99, right, for a good device.
So is there some relation like that between the base current and
And
collector
collector
or
current
emitter
or
current,
emitter
yeah.
current. We'll see. Let's see. So now let's start with the collector, no?
Yeah.
So I'll copy this picture. I think we will want it.
One thing is not very clear to me.
Uh-huh.
You are saying forward bias junction, there is some current.
Correct.
Most of this will go through that reverse bias junction. Huh?
Yes, that is correct.
I think I'll refer to some device textbook and
Correct. I think to go to that level of understanding,
Mhm.
a device's textbook may be needed.
okay.
Right? We will just assume that that current does flow through the collector.
Okay.
I know what you are saying
Hmm.
because we said that this. I'll highlight this. We said that this junction is reverse biased,
Yeah,
but there is still current flowing through the collector.
correct.
Correct?
Hmm.
Yes. So this operation of this device is not just like a PN junction. Even though we put two PN junctions together, there is something extra going on
Okay.
there. So maybe
I will check with some devices book.
sure. Okay.
Hmm.
So we said IC is alpha times IE, right? So now we also want to relate IC and IB.
Correct.
So what we will say, IC, now we will need to use another letter. What follows alpha?
Alpha, beta.
Beta. We will say something like this. So looks like the collector current is being related to the base and emitter currents,
Okay.
right? And now we can start
We can relate it in all ways.
in
all
many
the
ways.
Yeah.
See, but one thing we know,
Hmm.
there is no charge accumulation inside the device, no.
Hmm.
So there are three terminals.
Whatever current comes in, it goes out.
Has to go out. So one thing we should always remember. So IC plus IB, those are the two currents entering
Equal
the device.
to IE.
Should be equal to IE. Right? So this is something fundamental
Hmm.
to the device. This has nothing to do with alpha, beta and so on. Right? And people should also remember, we have taken two PN junctions, put it together, made the base very small.
Yeah.
But fundamentally, it's not going to produce power, electrical power.
Yeah.
Right? If it is only going to consume total electrical power, right? Just like diodes, right? So that is something also to remember. Okay. Oh, based on this equation, we can now create some relationship, no?
That is true.
Between alpha and beta. So, for example, IC is beta times IB.
Yeah.
So you can put these two together to say that IE is beta IB plus IB. So it's beta plus 1 times IB. This is another relation.
Correct.
Then we can say, we can put these two together, right?
Yeah.
So let us say IC plus IB is alpha IE,
Yeah.
right? Is 1 over alpha times IC. No? Is IE. I'll write it as 1 over alpha times IC. So then we can create a relationship between IC and IB again.
Correct.
So shall we say, we'll multiply throughout by alpha. Like this.
Yeah.
I just multiplied the equation by alpha. So then we said IC is beta times IB, no?
Yeah.
We'll write it in the same fashion. So alpha minus 1 IC,
Hmm.
right? I brought it to this side. Is this correct?
That's correct.
Or rather, we'll
Or
take
we
this
can-
one to the other
other
side. It is
side.
easier, no?
Yeah.
Because alpha is less than 1.
Correct.
So 1 minus alpha times IC is alpha IB,
Hmm.
right?
Hmm.
So which means IC is alpha by alpha minus 1 times IB, right? Oh, this is great. Now that means beta is
And-
related to alpha also,
Okay.
right? So it looks like beta is alpha by alpha minus 1. Oh, sorry, 1 minus alpha.
One.
I think I made a mistake.
1 minus.
I had
alpha.
1 minus alpha.
Correct.
Because alpha is less than 1, this cannot be negative.
Yeah.
Correct, perfect. So there are lots of relations like this, no?
Correct,
This is
correct,
nice.
correct.
So now you can also, so we got relationship between beta and alpha. We got relationship between IE and IB, IC and IB. So we can do this, right, between, with all of these.
But if I remember the first two, I can, or first three, I can make out of.
Correct. You use the first three, alpha, beta definition and the current, charge
That
accumulation inside
yeah,
the device.
yeah.
So
That we know even from KCL.
you know even from KCL. Correct. Nice. And we also said VB is VBE on, right? Now you can apply some other voltage, no? You are going to apply voltage to this device.
Oh.
So if VB is always VBE on, you may apply some other voltage at collector and so on. So that extra voltage must fall across the collector base, correct? So yes. And we need to make sure that it is reverse biased. Correct? So we need to apply enough voltage to reverse bias it.
So C cannot go below base voltage.
Base voltage, correct. So nice. So now we have a good understanding
Of the device.
Of the device.
As far as equations are concerned.
Correct. So that's right. That's right. So we can also say VCB should be greater than 0. Should we put that down somewhere? This VCB should be it should be reverse biased, no?
Yeah.
So VCB should be greater than 0. This is another condition. So that the device is reverse biased.
So when the junctions are like this, VCB is for reverse, the other one is forward.
Correct.
Is there some other name, region or something?
Ah, okay. So in that case, so we'll also write it like this. VB is forward bias, no?
Yeah.
So we'll just write that down separately.
Oh.
So if you do this, then the device seems to work properly, no? You have all of these currents.
Very active.
Very active. Oh, yes. So this is called the forward active region
Active region.
of operation. And it's called forward active. We will see that later. It's the active region. Many people just say active, right? Active region. We'll call it the forward active. We will explain what it is later also.
So there can be other combinations and then some other regions of operation.
That is correct. Well, we can see what happens when VCB becomes, forward bias.
Yeah.
We can see all of that. Correct.